Morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series, and we're going to be talking about span. Right, so this is more or less just a brief review of what span is. So previously we talked about vectors, and I'm pretty sure I wasn't able to record it. So I'm gonna talk about it for a bit. I'll talk about it for a bit. So basically what vectors are, they're a bunch of numbers that you can store in a very compact way, and you can do a lot of things with these compacted things. You call this a thing, you call this a vector, right? So you put the numbers into that vector, and you can do a bunch of stuff with it. You can multiply with a number, each of the components of a vector. You can do addition, and this definition here says we have a vector all the way to n components, and apparently there's a relationship between the number of components of a vector with its dimensional space. So say we have two components, then we're in 2D space. We have three components, then we're in 3D space. If we're in n components, in general, if we're in n components, then we're in n dimensional space. And we can write vectors in a vertical way, so we call that a column vector, or in a horizontal way, so row vector. And we can do a bunch of things with this, right? So these are just some examples here, some properties that we can use, which is very, very similar to the arithmetic properties that we learned in high school or even elementary. And then we dived into this concept of linear combinations. And what this basically means is this idea of adding two vectors together, right? And if we add two vectors together, we get a linear combination of those two vectors. And yeah, that's pretty much it. Oh, yeah. Also, another fun fact, I guess, is given some linear system, going back to chapter 1, we can actually express it as a linear combination of vectors. So we call this a vector equation. And that's it. And then some geometric intuition, which we didn't really go into too much since we already discussed that in my calculus series. So feel free to watch that. Okay, so moving on, let's actually talk about span. So span, well, we're going to open this section with a fictitious situation, right? So let's imagine that you live in the two-dimensional plane R2. And let's say we have this new car. So we have a car, right? So we have a car, and this car is delivered at the origin, and it's a simple vehicle. And at any given time, so okay, let me see. So it's delivered. Wait, how do we deliver a car? It's it's at the origin. We can imagine 2D as a place, right? Like a flat place. In this case, it's a plane actually, but we can imagine it as a place. So say we started at 0, 0, right? And at any given time, well, we can actually, can't read. Oops, what is it? Okay, we can actually point the vehicle in any direction. We can point car in any direction, left, right, up, down. It's a very, very fictitious situation, I know. Let's say we have these vectors here, 0, 1, or this u sub 2 vector here, 2, 1. We notice that these two vectors have two components, and so we can say that we actually are in R2. Both of these things, u sub 1, u sub 2, belong in R2. These are vectors in R2. Right. So this car can go in forward or reverse. So we actually, so my, I'm not gonna draw the vectors myself because the textbook already did this for us. So here we can see u sub 1 is 0, 1. And we can also see u sub 2 is that vector 2, 1. So we drew it in the two-dimensional plane. Now, despite its simplicity, there are many places in R2 that we can go, right? We can go to a lot of places in R2. For instance, we can go to 3, right? What does that mean? We can first traverse to 2 u sub 1, and then we add it to u sub 2, and then we can get to 2, 3. So all I'm saying is that we can go anywhere in R2. So for instance, so let's actually just not beat around the bush and let's just look at it this way. We can write a linear combination of these two vectors. 2 u sub 1 plus u sub 2, right? And this should give me, if we do the math correctly, with scalar multiplication and vector addition, we should get 2, 3. And what that looks like in the graph, or what that looks like geometrically, is this. There. So what happened to u sub 1? We just scaled it, so the vector became longer, right? So our magnitude increased for u sub 1. And for u sub 2, we just put it a bit up. And then we can get to this point 2, 3, right? This thing here is the vector 2u sub 1 plus u sub 2. That's that red vector there. Okay. And then we can keep doing this for a lot of different kinds of vectors. I'm not going to go through it, but that's the idea. Okay, let's do... Yeah, we can do more complicated paths. But basically, we can go anywhere, pretty much, in two-dimensional space. Right, let's do example 1. So let's show algebraically that this thing can actually reach any position in R2. So here's more of a showing thing. That car can be anywhere in R2. How do we know that this car can go anywhere in R2? So let's show it, right? So we can write a linear combination of these vectors. And it's going to give us any point A, B, right? So we can then translate this into a system of linear equations or an augmented matrix. Really up to us what we want to do. So this is the way to translate it to a linear system. And from there, we can say x sub 1 is b minus a half, and x sub 2 is a half. So that's the unique solution. And so we now know exactly how to find scalars x sub 1 and x sub 2 in order to reach any point A and B, right? So this is a unique solution. So this car can go everywhere in R2 basically, right? I hope that made sense. Okay, so what does that mean if it can go anywhere in R2? Well, the only reason why it can because we have a unique solution here. This is a unique solution, right? We can plug in anything for A and B. Say we plug in this 2 and 3, and then we can get these scalars, right? We can get these scalars. So what does it actually mean to go everywhere in R2, right? What that actually means is here we introduce it. So we can go everywhere in R2. So what does that mean? Like mathematically, what's everywhere? That means it's the span. So that's where the span comes in. Span of the given vectors that we had, u sub 1 and 2, the span of these is actually R2. Okay, now let's give a formal definition. So, the first time I looked at this, it was very tricky. So here's a formal definition for this. Five. Let's let the set of vectors u sub 1, u sub 2, all the way to m. These sets of vectors be a set. Okay, I'm just completing it. Set of vectors in Rn. So each of these vectors have n components, right? The span of the set is, so we denote it as this, the span of the set, right? And the span of the set, that's how we write it. It's actually the set of all linear combinations. Why do we say it's the set of all linear combinations? Because based on this example here, when we found a unique solution for A and B, to get such scalars x sub 1 and x sub 2, A and B could be anything, right? A and B could be anything. And so x sub 1 and x sub 2 could be anything. And so there are a lot of linear combinations, lots of scalars that we can use. These u sub 1 and u sub 2 vectors to get different kinds of resulting vectors. And so if we can go everywhere, and so we say that's the span because we can go everywhere in R2, then we say that's actually just all of the linear combinations that we can do given the two vectors that we have. Now, to generalize that idea, say we have a set of vectors, we get the span of those vectors in Rn, then it's just the set of all possible linear combinations that we can do for these m number of vectors, if that makes sense. So to mathematically describe this, it's actually just this is what we do when we're finding linear combinations, right? We multiply a scalar to each of the vectors in the set. And then we're going to get some resulting vector. I don't know. We're going to get resulting vector B. I don't know. Could be anything, honestly. And then here we say that x sub 1, 2, all the way to m we say these are real numbers. So these aren't vectors, these are scalars, which are real numbers. Let's actually write that out. Right. Let me go here because I'm putting all my definitions here. Yeah. So now we're adding this to our toolkit, right? We're going from linear equations to augmented matrices to Gaussian elimination, how to solve these linear systems. What is a solution? What is a solution set? What are vectors? And given these vectors, what's the span of these vectors? How does it relate to linear combinations? And a bunch of stuff like that, right? Okay, so here we say that if the span of a set of vectors is indeed Rn, this is a very general statement. We just say, okay, this is a very general statement. We just say the set, so this is actually just another way of saying it. The set of these vectors spans Rn, right? So that's what that means. Okay, I hope that made sense. That because that one's very, very critical to know. Okay, let's actually now look at a more down-to-earth example, which is a span in R3. So this is from Calculus 3. So suppose, say we have these vectors, u sub 1 being or having components 2, 1, 1. Another way we can write it is like this. This is more of a physics notation. And I decided to write it as a column vector. Then we also have u sub 2 here, which has 3 components, namely 1, 2, 3. So what's the span of these two vectors? The span of the set of these two things is the set of all linear combinations of all linear combinations in the form, so we say x sub 1 could be any, right? Could be any scalar. X sub, oh shoot, x sub 2, then multiply to that u vector equals some value, some vector, I mean. So here's something I'd like to point out is that some vectors in R3 are in this span. Some vectors in R3, while some are not. Maybe a fact, fun fact. So some vectors in R3 are in the span of the set of these two things, these two vectors, while some are not. And that depends if we can write the vector, say that vector W, is that in the span? If we can write it as a linear combination of u sub 1 and u sub 2, that's how we'll know if it's in the span, right? Because we know u sub 1 and u sub 2 are in R3. They're in the span of R3. They span R3. Okay, let's give an example. Here we want to show that v sub 1, so this is a vector, and it has 3 components, is in this span of, I think it was u sub 1, u sub 2. Yeah. Can we say that this one is in the span of u sub 1 and 2? And v sub 2 is not. So let's actually walk through this together. So the only way to determine, we can determine if, okay, I'm going to write this a bit mathematically. If v sub 1 is in the span of u sub 1 and u sub 2, if, or if and only if, we can write v sub 1 as a linear combination of the two vectors that's actually in the span. Right? So let's translate that. So u sub 1 can be expressed like this. U sub 2 can be expressed in their actual vector, 1, 2, 3. And v sub 1 is negative 1, 4, 7. So if we manage to find an x sub 1 and x sub 2, these scalars, then there is a linear combination. And if there is a linear combination, then we know its part. Right? So the way I would do this, you could, so this is, we talked about it, it's a vector equation. But we can write this in an augmented matrix form. And then we can do Gaussian elimination and all of that tedious stuff. Let's actually do it. I'll do it. 1, 4, 7. Okay, we keep going. So I would subtract row 2 to row 3, put that in row 3. So here I'll try to speed it up a bit since you already learned this. 2 minus 3 is negative 1, negative 3, 1, 2, 4. Let me make this a 1. I'd multiply a half to R1. That gives me a 1. Subtract it to R2, put it to R2. This one stays the same. This one changes. 2 becomes a 1, a half, negative a half. 1 minus 1, 0. 1 half minus 2. So that's negative 3 halves. Then we have negative a half minus 4. So that's negative 9. And then we could multiply these two things by 2. This becomes 2, 1, negative 1. You could even multiply that. So I'm doing 2 steps here. I'm multiplying everything by 2 just to get rid of those fractions. Negative 3 and, negative 3 and 9. Ooh. So what I could do, I could multiply it by 2 divided by 3. So multiply it by 2 divided by 3. That gives me a negative 1 and a 3. Right? Okay, now we have a very, very interesting situation here. What can we do now? Well, for one, I could make this thing positive, R2, and then we add it to R3, put it in R3. And I think we should have it in echelon form. So this is going to be 0, 0, 1 minus 1, 0. This is 1. Negative 3 minus 3. Interesting. -9. This has no solution currently. Is it in the span? Or did I mess up something? Probably messed up something. Oh, I did mess up something. Okay. Okay. 1, 2, 4. Did I mess up on? Wait a minute. I started off with the right matrix. Then somehow I lost it. Let me see. Row 2 minus row 3 is row 3. Okay, correct. Okay, I think this is where I messed up. Let's try again. So I want to get rid of this one here. So I would do a half of R1 minus R2, put to R2. Okay, this gives me a 1, 1, 1 half, negative 1 half. 1 minus 1 is 0. 1 half minus 2 is negative 3 halves. And then, where is the one? Negative 1 half minus 4. 4 is 8 over 2. Minus 9 half, right? Okay, let me do an extra step here. So I'm going to multiply 2 to R1 and 2 to R2. So this gives me a 2, a 1, negative 1 back. This gives me 0, 0, 3. Gives me negative 3, negative 9. Oh, so I did mess up a bit, yeah. And then this gives me 2, 1, negative 1, 0, 1, 3, 1, 3. Okay, there we go. Yeah, so what I did here was negative of R3, put it to R3. And then I think I did negative 3 of R2. And I put that to R2. Okay, so we're back on track. And then from there, I could just say R2 minus R3, put to R3. Because then I would just get 0, 0, 0. So this is an echelon form, right? Leading terms are to the left. It's in descending order. All the 0 rows are at the very bottom. And no issues with anything so far. Yeah, it's an echelon form. So back substituting this, we say that x sub 2 is 3. Then 2 sub 1 plus x sub 2 is 2x sub 1 plus 3 is negative 1. So we say x sub 1 is negative 2. This is minus 4 divided by 2 minus 2. Yeah. And we got it. So we say that there is a linear combination and that is negative 2 of u sub 1 plus 3 u sub 2. And if we do that, we're going to get v sub 1. So v sub 1 is part of the span of u sub 1, u sub 2. And we pretty much do the same thing for v sub 2. Oh, we didn't say what v sub 2 is. 8, 2, 1. So this one isn't. because we're not going to be able to find anything. You can try. Let's see. I'm just going to skip all of the shenanigans. Let's just go through it. 821. Yeah, I just shortcutted all of that. So this, I'm going to say there's no solution, but we'll see. Let's keep doing Gaussian. So I could say, actually, we can do the same thing. So we do, what do we do? R2 minus R3. So this stays R2 minus R3. We put that in R3. 1 minus 1, 0. 2 minus 3, negative 1. 2 minus 1, 1. Right? Okay. And then keep going. What was my next step? A half of R1 minus R2. We put that in R2. So this would give me half of R1. So this is 1, half, 4. 1 minus 1, 0. Half minus 2 is negative 3 halves. Half minus 4, 2, 3 halves. Yeah. And then 4 minus 2 is 2. Let me keep going. What did I do here? I did, I scaled it back. So I multiplied 2 to both R1 and R2. So this would be a 2, 1, 8. This would be 0, negative 3, 4. Times 2, 4. And that's it. 0, negative 1. Oh, this is 1. 2 minus 1 is 1. Then now I can do this. So negative 3, starting to think there is a solution, but we'll see. So here we have, what can we do? We can multiply by a third to R2. That would give me a positive 1. Then I add it to R3. Then put that in R3. Then I can do this. 0, 0. This puts me at 1. This puts me at negative 4/3. Okay. 1 minus 1 is a 0. Negative 4/3. There's the issue. Add it to 1. Negative 1/3. Here we can see there's no solution. Right? 0, it's in the form 0 is equal to negative 1/3. So that's just no solution. So no solution since there is no linear combination that would give me V sub 2. So V sub 2 is not in the span of the two given vectors U sub 1 and U sub 2. Right? Okay, cool. So lots of notation, a little bit of notation. Yeah, that's pretty much it. Great. So another way to visualize the span of two vectors in R3 is if we actually get two pieces of string and we tie them to some solid object like a refrigerator, and we get the friend to pull the strings tight in different directions. So the strings are the vectors. And next we get a lightweight flat surface pizza and gently rest it on the strings. And we think of the surface as a plane, then the span of the two string vectors is the set of all possible vectors that lie within the plane. And note that no matter the angle of the strings, if you're doing this correctly, it's possible to rest the surface on them. Okay? So this is a span of u sub 1 and u sub 2. Let me just show you. So its span will give us some shape. In this case, it's a plane. It's not specifically all of R2, or all of R3, I mean, but it is a plane, u sub 2 and u sub 1. And at some point there, at, at some point there, v sub 1 is part of the span while v sub 2 isn't. So we can write a vector that's part of the span here, while there are also other vectors in R3 that we can't. Right? So let me show you another one. So here's another example of geometrically how this looks like. Here we have three things. So here we say this is the span of u sub 1 and u sub 2. Right? This here, A, is the span of u sub 1, u sub 2, u sub 3. Here we say that u sub 3 does not belong in the span of u sub 1 and u sub 2. Right? It's literally not part of the plane. You can see it. Okay, just some geometric intuition behind it. Okay, let's talk about three vectors in R3. So later in the section, we will show that no two vectors can span all of R3, but three vectors can. So let's just put that out there. So if we're given two vectors, we're for sure not going to span all of R3. Right? But three vectors can. Right, let's do an example to start off. So here we're being asked to show this v vector, which has components 5, 2, 1, is in the span of u sub 1, u sub 2, u sub 3. And then we show that the span of u sub 1, u sub 2, u sub 3 is all of R3. Because what we stated earlier is that we can. We just don't know how. But the textbook says we can, and we just agree with it for now. Right? So how do we do it? Well, let's start with the first one, right? So again, to show that a vector is part of a span, right? We have to check if we can write a linear combination of these three, which would give us the resulting vector v. So we have to say x sub 1 times u sub 1 sub 2 u sub 2, x sub 3 u sub 3. Can we find a linear combination of the three vectors, which will give us the resulting vector v? Right? Oh shoot, my bad. I forgot to show what u sub 1, 2, and 3 are. Let me just show them real quick. So u sub 1 has components 2, 1, 1. U sub 2 has components 1, 2, 3. And u sub 3 has components, I think it was 9, 1, negative 1. I want to show this. So I'm immediately going to write it as an augmented matrix. I'm not going to waste time. We have 2, 1, 1. And then I think it was 1, 2, 3. That was 9, 1, negative 1, which would give us the resulting vector 5, 2, 1. Now we do Gaussian elimination, we do elementary row operations, and we see, right? So let's do row 2 minus row 3. 2, 1, 9, 5, 0, negative 1. Ooh, 2, 1, 1, 2, 1, 2. Okay, let's keep going. So what can we do? Divide row 1 by a half, subtract it to row 2, put that in row 2. So leave row 3 alone. This one becomes a half. So 1 half, 9 half, 5 half. 1 minus 1 is 0. 1 half minus 2 is negative 3 halves. 9 half minus 1 is 7 halves. 5 half minus 2 is 1 half. If that is correct. Yeah. Then what I would do here, I would multiply 2 to R1 just to keep it simple. And same thing with R2 because I can. So this becomes 2, 1, 9, 5. 0, negative 1, 2, 1. Same idea. And then 0, negative 3, 7, 1. Right? Okay. And then, well, we can't apply row 1 to 3 because then that first 0, the bottom left 0 is going to be a non-zero. So we have to do something with row 2. And we can multiply negative 1/3 to make it 1. And then we're going to add it to row 3. And then we apply that sum to row 3. Right? So leave row 1 alone. There's a 9. This we leave alone. Negative 3 becomes 1. 1 minus 1 is 0. 7/3. And then 1/3. Negative 1/3. Negative 7/3 minus 2. So this gives me 13. Oh, not minus 2, plus. Whoops. This gives me negative 1/3. And then negative 1/3 plus 1. So that's 1 minus 1/3. That's 3, 3 minus 1/3. That's 2/3. Then I can make these nicer looking numbers. I can multiply 3 to row 2 and 3 to row 3. This becomes 0, 3, negative 7, negative 1, 0, 0, negative 1, 2. So now it's in echelon form. So we can find solutions for this thing. So we do a back substitution. Negative x sub 3 is 2, so we just say x sub 3 is negative 2. And then we have 3x sub 2 minus 7x sub 3, which is the same as 3x sub 2 minus 7 times negative 2 is negative 1. This becomes 14 minus 14. Add the 14 to the other side. 1 minus 14 is negative 13. 9 divided by 3. So x sub 2 is negative 13 over 2. Why is there the showing there? And lastly, x sub 1, or 2x sub 1, plus x sub 2, plus 9x sub 3, if that's correct. Yeah, which is just saying, so x sub 2 is minus 1, minus 13 over 3, plus 9 times negative 2. This is equal to 5, right? So we just continue. Minus 18, 5. We add 18 plus 5, 23, right? This becomes 23. I add 13 over 3. Oh, I need a calculator for this. Okay. So, right, what we do? We did 18. We add it. We got 23. And we add 13 over 3. We got 69 over 3. We got 82 over 3. So we actually got, there we go. Then we divide 2. So we multiply this by a half. 82 becomes 41. So x sub 1 here is 41 over 3. And since we have a linear combination that we can write to get v, then we know v is in the span. See if I got that one. Or I didn't. Probably didn't. Oh, what's this? 211. Okay. Okay, got a different one. And there's nothing wrong with checking, I would say. It's fine. So we got 41 over 3 of u sub 1, or just in case minus 13 over 3 of u sub 2, minus 2 of u sub 3 is just v. And we can, I don't want to show it, but it's probably correct. So v is in the span of the 3 vectors, or the set that contains 3 vectors, to be precise. Okay, cool. Okay. It gave me a different answer, which is weird. But I guess I should be fine. I probably got different solution. and the textbook got a different solution. I don't see any mistakes I did though. That's the thing. One way to check it would be to multiply all of these to actually do the scalar multiplication and vector addition to see if we get the v. I'm not gonna do that now, but I'll do it sometime. Okay, so that's part one of it, right? So we show we show that v is part of the span. Now, how do we know that the span is actually R3? So now we to show that the span of these things is actually just the whole space R3, then we can plug and play. We look at the set of linear combinations that we can do, right? And see if we actually get some arbitrary vector ABC, which is, this is an arbitrary, this is any vector in R3, right? Let's see. Okay, so let's immediately do augmented matrix, right? I'll copy paste this thing. Oh god, you're telling me to do all of that? That's okay. I'll just skip through all of it. A, B, C. So if we actually do a lot of these stuff, we're gonna get this matrix here, which is 1, 2, 1, 0, 1, -2, 0, 0, 1. Then we get A minus 5B plus 3C. Then we get minus B plus C, or C minus B. And here we get B. So in fact, there is a solution. Back substituting, we can get x sub 1 to be negative 5A plus 28B minus 17C. Then x sub 2 is going to be 2A minus 11B plus 7C. Then x sub 3 is going to be A minus 5B plus 3C. So there is a unique solution. So if we plug in any ABC here, we're going to get the corresponding vectors x sub 1, 2, and 3. So since there is a unique solution and we can get all the linear combinations we can just by modifying these scalars based on our input from ABC, then the span these two things, or these three things, is actually just the whole R3. Right? Okay, so that was a lot to take in. We are far from done here. Yeah, a little bit far from done. I'm gonna take a short break on this. I'm gonna continue with, what's this? A theorem here. But yeah. I hope you guys enjoyed. So this is just a little break. I hope you guys enjoyed, learned a lot. and I'll see you all in the next one.